Hello, this is the video for Unit 1 Limits and Continuity from AP Calculus AB and BC. Now before we begin, we have to ask ourselves what exactly is a limit. Now a limit is the value that a function approaches when x is a certain value. Now let's see this with a graph. So we can see in this graph, we can pick any arbitrary point. We can pick, say, x equals 2. And both sides of this graph approach -1. They approach -1 as this graph approaches x equals 2. That's that point right there. Now, we can look over here at -3, whereas there's this hole right here in the graph where the curve passes through, and instead, this filled in dot is here at somewhere in between -4 and -5. Now, a limit says that the limit of -3 is not this dot right here with x equals like -4. It's this right here, this y equals -5. And the reason that is because a limit is the value a function approaches, not what it actually is. On both sides of this curve, the value approached is around -5. It's not this dot up here at -4. That's why the limit in this case is here at -5. We can see a few more examples of this. Let's pull up a few more graphs. We can see a graph that looks like this. Now here, we would say that, well, from the left side, let's say the negative x side, we're approaching -3. As we approach 4, x equals 4, we're approaching -3 as our y value. And from the right-hand side, the positive x side, we're approaching +5 as x becomes 4. And since these limits are different from each side, we said there is no limit. Even though the function is defined at this point, down here at -3, we say that there is no limit because the function is not approaching a single value. Now, we can also represent this in terms of tables. Right, now looking at this table, let's see. As we approach 6 from the negative side, we approach -6. Right, we approach -6. But from the positive side, we approach 5. So this is another case. Now on each side, the limits approach different values, so there is no one singular limit. Now, there are limits that are defined, obviously, like this one. As we approach 1 from both sides, from the negative side, we approach -6, and from the positive side, we also approach -6. As you can see, the values are continually getting closer to -6. And that's what a limit is. We really don't care at what the value of f of x is at x equals 1. We care what the value of f of x is around x equals 1. That's why we can find the limit from just these tables. We don't need the actual x value, the actual y value at x equals 1. Now, saying that, let's bring in these. These are the limit laws. Right, now that you know what a limit is, these are how limits can be modified. Now, it does seem like a lot, but the main takeaway from all of this is that you can apply just about any operation to a limit, and you can basically just split up a limit, right? You can see when you have a constant times f of x, you can pull the constant out, and then just do the limit at f of x. You can see if you're trying to add two functions and take the limit of that, you can just take the sum of the limits. You can take the difference of limits when you're taking the difference of functions. When you're multiplying functions, you take the product of their limits. And every single one of them on here just shows that you can split up the components of limits. Right? When you take f of x to the power n and take the limit of all that, well, that's the same thing as taking the nth power of that limit. So these limit laws, they're useful and they're a bit of common sense, right? You can always just take f of x plus g of x. Well, you can just split it up, do it twice. And those are the limit laws. Let's see what we can do with a different subject. This is about continuity, the second part of this unit. Now, here's a graph. And looking at the graph, does it look continuous? And I mean, you might be tempted to say yes, because the curve, like, it doesn't like jump from one place to another, but also there's this hole right here, and the actual value is up here. And that makes this discontinuous. It's not continuous. And then we can see how we can determine if something is continuous or not using three pretty simple rules. Alright, so let's do this. These are the continuity rules. So the rules are that at x equals a, well, the function has to be defined, right? There has to be a point. Now, bringing our graph back that we had before, looks like this. This fulfills the first criteria, right? It is defined at f equals a. I mean, at x equals a. It is f equals a equals 3. It equals 3. That's what this dot right here is. And then they're saying, well, the limit of f of x has to exist. Well, looking at this, the limit does exist. On both sides, as we get to x equals -5, we approach x equals -3 from both the left-hand side and the right-hand side. So that limit does exist. But the last criteria is that the limit has to equal the value of the function. Right, now looking at this, well, the limit is -3. And the value of f of a at -5 is +3. And these are not equal, so it doesn't fulfill this criteria. To be continuous, this function has to fulfill all three of these criteria. And because it messes up on one of them, it is not continuous. Right, let's look at some other ones, some other examples. So here's another graph. And right off the bat, you have probably already figured out that this is not continuous because of this jump. And you're right, it's not continuous, and it is because of that jump. And the reason that this jump makes it not continuous is because of the second criteria right here, that the limit has to exist. The limit, as we approach from the left-hand side, equals 2. The limit as we approach from the right-hand side equals -2. These are not equal. If your left-hand limit and your right-hand limit are not equal, then your limit does not exist at that point. So the second criteria is not true. And therefore the third criteria is also not true, because if the limit doesn't even exist, it can't be equal to anything. And then f of a is defined, it's -2, but that doesn't matter because we already violated some of the criterion, so this cannot be a continuous function. Now let's look at a function that is continuous and see what that looks like. Now this function is continuous, right? F of a is defined, right? It's down here at -5, y equals -5 at x equals 6. So this is true. The limit also exists from both the left-hand side and the right-hand side. We approach -5. So the limit also exists. And since f of a equals -5, and the limit, the curve approaches -5 as we approach x equals 6, these two values are equal, and therefore this third criteria is satisfied. So all three of these criteria are satisfied, so the function is continuous. As you can see, there's no break. There's no break in the function, there's no holes anywhere, it doesn't jump. This is a continuous function. Now, with that being said, let's look at a different depiction of continuity. This is a very common one on AP exams. Instead of using a graph, where it's often pretty easy to find discontinuities, right? You just look if there's a hole or a jump. We can use functions. Now, they will, on the AP exam, they will ask you this kind of question where they'll just give you a function and ask you, is it continuous? Why or why not? And it's your job to just find out if it's continuous, and if it's not, then just find out why not. Which of these criteria is not satisfied? Now let's see. If we try to look at f equals a at, well, the break here is at -3. So the question is, at x equals -3, is it continuous? Now at -3, we have this value right here. You can put the natural log of the negative of -3, which is 3, plus 3. Well, that's equal to the natural log of 6. So that is, f of a is defined. f of a is defined at x equals -3. Now we have to find out if the limit exists. Now the limit from the right-hand side is obviously also the natural log of 6, because what we just did was plugging in this -3 value into the second function. And the second function is the right-hand value, because you can see for the first one, it goes -infinity all the way up to -3. And the second one goes -3 up to +3. So this is the right-hand limit, and it's the natural log of 6. Now we have to find out if the other one also satisfies this. Also is -6. I mean the natural log of 6. And we can just plug in the value, right? We plug in -3 into ln of -x plus 3. Now even though this is a strict inequality, x equals 3 does not follow this, then you have to plug it in to find the limit, because this is approaching -3. It gets like all the way to -3, but doesn't actually have the value at -3. So to find the limit, you just plug -3 into here and see what you get. Now if you do that, you have natural log of -x, or -3, which is 6. Which is 3. 3, and then you add 3. And this is not equal, right? If you remember the logarithm laws, you can see that if you combine this ln 3 plus 3, it would be the natural log of 3e to the third power, which is not 6 in any way, shape, or form. So these are not equal. Like these left-hand limit and right-hand limits, they're not equal. So the second criterion is not true. And therefore the third criterion is also not true, because you can't have something equal when it doesn't exist. So this is not continuous. And if you were to write an explanation about why, you would say it's because this left-hand limit and this right-hand limit, they're not equal. Therefore, the limit doesn't exist and it violates this criterion, so this function cannot be continuous. I hope you enjoyed this video. I hope you learned something from it. And if so, I'll see you next time.